guys, today's screencast is on Earth motions. So it's all about the Earth and how it moves in our solar system. Uh, First, we need to distinguish the different types of motions, I suppose, right? Because the Earth is actually doing two different things at once. It's both rotating and it's revolving. So when we talk about rotation, we're talking about the Earth spinning around on its imaginary axis, right? In one day, 24 hours, it does one complete rotation, 360 degrees. Now, simultaneously, as we're rotating, we're also revolving, or we're orbiting around the sun. Every 365 days or 1 year, we make one complete revolution. So this animation does a nice job of showing the difference between those two motions. Notice the Earth is spinning around like a top. That is rotation, while it's moving around or revolving around the sun. So they are two very different motions. Although some people use those words interchangeably, they are very different. Rotation is spinning around on its axis. Revolution is moving around the sun. Today's screencast, we're going to focus on rotation. How do we know the Earth rotates, and what is the evidence for Earth's rotation? So here are the sort of the motions of rotation, I guess we could say. We know the Earth is spinning around on its imaginary axis of rotation. That is, if we were to take a stick and stab it through the North Pole and it pops out the South Pole, that's the axis that the Earth rotates on, right? Notice that it's slightly tilted, right? It's not perpendicular to the plane of its orbit. Rather, it's tilted by about 23.5 degrees. The direction of rotation can be described as, if we were looking down at the North Pole, as counterclockwise, or if you grab sort of the west coast of North America and pulled it towards the east, it is rotating west to east. Now that west to east rotation is actually really important because as a result of that west to east rotation, stars appear to rise in the east and set in the west. And whenever we look at the sky and whenever we see a celestial object such as our sun or any star or even our moon, because of that west to east rotation, those objects move in the sky and rise in the east and then set in the west. And that's a predictable pattern. And it's not as though these objects are moving in space like this. It's because the Earth is spinning west to east, giving these objects an apparent rise in the east and set in the west. We can actually visualize this with another animation that helps us see this rotation. Now this is a space perspective of the Earth. It's a side view. You can see how the Earth is rotating counterclockwise or moving west to east. And when we look at a side view, it's pretty interesting because we can see that half of the world is illuminated or in the light of the sun, while the other half of the world is consumed in darkness. Right? And so the Earth is going to be rotating in and out of this darkness and daylight. You can actually identify specific times on planet Earth, right? So this line of longitude closest to the sun is going to be solar noon. The opposite side of the Earth, this line of longitude here, will be midnight. And then we have a boundary here between daylight and nighttime, and of course this represents 6 p.m. or sunset, right? Because it's daylight and it's moving into darkness. Now, if we could see the other side of the Earth, the darkness is then going to be rotating into daylight. Well, that would be about 6 a.m. or sunrise. We can also look at this from a polar view. You know, imagine if you were standing over the North Pole. Again, take a look. West to east rotation or counterclockwise. The dark portion is rotating into daylight. This would be solar noon closest to the sun. The side opposite would be midnight. Right here, we're rotating into darkness. This would be sunset, as it's light and going into dark. And right here would be sunrise, as it is dark rotating into daylight. We can also calculate how quickly this is occurring. And I think we've done this before this year, but we can determine the rate of rotation if we know a couple values, right? We know one rotation equals 360 degrees. That is one complete spin. How long does that take? Well, one rotation takes 24 hours. So if we want to know the rate of rotation, we need to simply divide the number of degrees that the Earth rotates by the time. That is a rate, which is 24 hours. So in one spin, 360 degrees, it takes 24 hours. If you were to plug and chug then, we'll include our units here, that equals that magical rate of rotation of 15 degrees per hour. And if you guys recall when we talked about time zones earlier this year, every 15 degrees change in longitude represents 1 hour time change. And of course, depending on the direction that you travel, if you're going west, you subtract those hours, and if you're going east, you add those hours. Those are our time zones, right? And that's all based on Earth's rate of rotation. How else do we know that the Earth rotates? Aside from having a day-night and that sort of predictable cyclic pattern, there are some other really interesting clues that allow us to understand that the Earth is rotating. One is called the Coriolis Effect. And this is sort of an apparent deflection of anything that's traveling over Earth's surface a great distance. For example, prevailing or global winds, ocean currents, planes, or even like guided missiles. All of these things get deflected, or at least apparently deflected, because the Earth beneath them is rotating or spinning, right? So imagine this, you're standing at the center of a merry-go-round, and then someone is at the edge of a merry-go-round. And then you try to throw that person a ball, but that merry-go-round is rotating. So if you try to throw it in a direct path to that person, well, that person isn't going to be at that same location by the time the ball gets to that position. And so as a result, that ball will have appeared to have deflected. Now, depending on what hemisphere you're living in, you get different apparent directional deflections. For example, if you're living in the northern hemisphere and you tried to shoot a cannon straight to the north, well, you might notice that by the time that cannonball gets there, the Earth will have rotated, and so it will have appeared as though the cannon and the cannonball will have deflected to the right. Now, that's very different for the southern hemisphere, so if you tried to shoot that same cannon to the south in the southern hemisphere, it will have appeared to have deflected to the left. Alright, I think it's actually really helpful to see this in motion. So I have an animation of this, and let's take a look at it. Okay, so here's an animation of planet Earth, and we are going to take a flight. Alright, so we're going to actually start way up here in Alaska. So we're in the northern hemisphere, right? And we're going to try to take a flight by flying in a straight path to Florida, Miami, Florida. Now, if we do not account for Earth's rotation, and if we try to fly in a straight path, we are going to miss our target, and this will illustrate the Coriolis effect. Alright, so I'm going to press play. Here's here's our starting point. This is our target. We're going to try to fly straight, but the Earth is rotating. Whoops, we missed our intended target. Notice the direction of reflection. Since we're in the northern hemisphere, we have missed our target to the right. And no matter what direction you're traveling in the northern hemisphere, the Coriolis effect always causes these motions to deflect to the right. Alright, well, let's take a look at this, a similar example, but this time now we're in the southern hemisphere. Alright, this time we're going to be in Tierra del Fuego, Argentina, and we're going to try to fly to Rio de Janeiro in Brazil. So we're going to fly north in the southern hemisphere. Here is our starting point. There is the target intended path. If we fly straight, whoops, we have missed our target. And this time, since we're in the southern hemisphere, we are missing our target to the left. So again, the Coriolis effect causing these long distances to be deflected to the left in the southern hemisphere and to the right in the northern hemisphere. And this is especially notable when we look at planetary winds and ocean currents. Okay guys, so why don't you go ahead and pause the screencast for just a moment, and there are 4 arrows in your notes which you are to draw arrows to indicate the direction of movement for winds in the northern hemisphere relative to the arrows drawn. Alright, so aside from the Coriolis effect, we have the Foucault pendulum, which is a second line of evidence for how we know that the Earth rotates. Hundreds of years ago, there was this French dude by the name of Jean Foucault, and he was very rich, and you know, what do you do when you have a lot of money? Well, you build a big pendulum in your basement, obviously, right? And so Jean Foucault actually built this pendulum, which was like a suspended weight from a suspended platform, basically in his basement. And what happened was is that this weight just sort of swings back and forth, and it's on its own independent plane, and so it just continues in this fashion indefinitely. Now, this pendulum will keep swinging back and forth, and you would think, all right, well, it's on its own plane, it should just keep swinging back and forth in the same direction unless it is influenced to move a different direction. Well, what happened was is that the pendulum continued to swing in that same direction, but when he came back a few hours afterwards, after he grabbed a hamburger or something, he noticed that the pendulum appeared to change direction. But the thing is it wasn't the pendulum that changed direction, it was the Earth beneath it that rotated. And since the Earth is rotating counterclockwise, it gave the pendulum an appearance of clockwise rotation. So you can actually see some of these pendulums in certain museums. There's one in Toronto, and what they do is sometimes they set up all these pegs around the pendulum. And as the pendulum swings back and forth, it knocks those pegs down. And since it's going to be changing directions because the Earth beneath it is rotating, it knocks the pegs down in a clockwise pattern. And here's what it sort of looks like. Notice that the pattern created by the pendulum is moving clockwise. You guys see that? Now, because that is moving clockwise, or the reason it is moving clockwise, is because the Earth beneath it is moving counterclockwise. So here it is. Notice the apparent motion of the pendulum is swinging clockwise, while the Earth is moving counter. I think the best way to illustrate this is to take a pencil, and you guys will see a circle in your notes with all of these letters. What I'd like you to do is place your pencil across the circle so that the pencil is covering letters A and E. And while you have it covering A and E, you're going to carefully rotate the paper counterclockwise, because that represents the Earth spinning counterclockwise. But you need to keep the pencil parallel to the edge of your desk while you do it. So go ahead and pause the screencast and try this out. Alright, additional clues. When we look up at the sky, we know the stars aren't static. They don't remain in the same location. Throughout the night, they appear to move. In fact, those stars are moving counterclockwise because the Earth is also rotating counterclockwise. Right? And we have what we call circumpolar stars with one star at the center because it's located directly over Earth's axis of rotation. That star, of course, being Polaris. Well, here's what kind of cool, fancy photography trick is that some photographers who are really slick know how to keep their camera shutter open so they can capture motion. How cool is this? And so they leave their camera open at night as it's angled towards the stars, and over a several hour period, they catch what we call star trails. So these star trails are showing the apparent motion of the stars as the Earth is rotating. And what's really neat is that as these stars rotate, they create these trails which we can measure to determine how long that camera shutter was left open. Because the angular distance of this will represent time. And if we know the rate of rotation, we can figure out how long we left the camera shutter open for. Let's try one out. Here we have a scenario where we have 3 star trails. And you notice that the star trails have an angular distance, right? So this is the sky. And we have different stars. So here's 1 star, here's a 2nd star, here is a 3rd star, right? And we can measure the angular distance because the first star travels from 0 degrees to 60 degrees. What about the 2nd star trail? It goes from 90 degrees to 150. What's the difference between those two angular measurements? 60 degrees, the same angular distance from 0 to 60. And then what about this one? 240 to 300. The difference there being 60 degrees as well. So all 3 of these stars were captured, and they all show a 60-degree angular motion. Now you'll notice, okay, but this star looks like it's longer, right? It looks like a longer star trail. Well, that's because it's further out away from the center. The closer you are to the center, the shorter the trail appears. Yet it's still traveling the same angular distance. This is 60 degrees, and this is 60 degrees. Well, can we figure out how long the camera shutter was left open? Well, if we know that star trail 1 is 60 degrees, how many hours was the camera shutter left open? Well, if we know the rate of rotation is 15 degrees per hour, we can simply calculate it by dividing 15, the rate of rotation, into the angular distance, which would ultimately give us 4 hours. Right? So over a 4-hour time period, the camera shutter produced a star trail that traveled 60 degrees. Go ahead and try the next one. You may want to pause the screencast for a moment. Alright guys, well in this particular case we have 3 star trails again. Star trail 1 is 30 degrees. Moving to an angular distance of 30 degrees. Star trail 2 is going from 210 to 240. Guess what? That's also a 30-degree difference. And star trail 3 is going from 300 to 330, also a 30 degrees. So all 3 of these star trails were created from a camera shutter that captured star trails traveling 30 degrees. Well, we know the angular measurement, we know the magical rate of rotation. How many hours was the camera shutter left open for? 2 hours. 30 divided by 15 gives us 2 hours. Alright guys, that's it for today. You're going to start your homework and we'll see you tomorrow.